Alright, we are back. This is Stats 189. We're looking at Chapter 11. Notes. So there's two things in Chapter 11 that we need to take a peek at. It's the test, the chi-square test for goodness of fit, and then also 11.3 ANOVA. So the ANOVA is more going to be interpretation than anything. So first let's take a look at the goodness of fit. So what that is it's a way to see if data fits. Either you can do a test for normality, that's a little beyond the scope of our course, but it's more like, does the observed match the expected? And we do it with a hypothesis test. So just like the other hypothesis tests that we've run, the chi-square, so this is 11.1, the chi-square looks like this. That's unfortunate because then a lot of people think that that means you square the result. It doesn't. That's its name, is chi-square. And the way you find the chi-square statistic is you do observed minus expected, you square that result, and then you divide it by the expected. And then what you do is for each different category, you sum that up. So that's what that little, the sigma means in front of it, the capital big, or epsilon rather, big capital epsilon. Right tail test degrees of freedom is the number of categories minus one. So there are degrees of freedom, just like with the T distribution, the chi-square has degrees of freedom, and degrees of freedom are equal to categories minus one. All right? So if we said, hey, we have data of black cars, silver cars, or other colors other than black or silver, observed was 70, 40, and 70. But we expected that they'd all be the same with 180 cars, so it would be 60, 60, 60. And so let's see what this would be. So degrees of freedom would be, there's three categories, minus one. So we have 2 degrees of freedom on it. And so we can look up the degrees of freedom. It is skewed. But if we were going to do a test at the 5% significance level, so they'll give you that, they'll give you the significance level, we want to know the critical value, like the cutoff, like what we have to beat in order for it to be, you know, observed and expected. The null and the alternative hypotheses for these are maybe a little easier than what we've done in the past, because it is just, there is no difference or there is a difference. So no difference, there's no difference between the observed and the expected. And then the alternative is there is a difference. It does not fit the expected distribution. All right, so then if we're going to find our chi-square, first let's look up the statistic. And so we get out our important formulas sheet, and we look up chi-square. So that is table G. And we go to 2 degrees of freedom at 5%. So 5% on the top and then down to 2 degrees of freedom. It's 5.991. So we're still doing the like kind of the 5 parts. You have your hypothesis, you have your draw the pretty picture and mark the critical value. So if it ends up in the shaded area, we reject the null and say it is different than expected. It doesn't fit. If we end up in the unshaded area, less than 5.99 for our statistic, then we say we fail to reject and say there is no difference. All right? So let's do C, find the statistic. So the chi-square statistic itself would be the summation of observed minus expected squared divided by expected. And so let's see, we have just 3 observations. So here, we can do this right here. 70 is the observed, minus 60 is the expected. You square that result and then divide by the expected. Plus 40 minus 60 squared divided by 60. And then, same one, 70 minus 60 squared divided by 60. Sorry, I had to kind of write downward here. So what is that? That is 10 squared, that's 100 over 60 plus negative 20 squared. Oops. So negative 20 squared is actually 400 over 60. And 10 squared is 100 over 60 again. And so when you look at the chi-square statistic, this is going to be 1.6 repeating. This is going to be, what does that work out to be? 6.6 repeating. And this is 1.6 repeating again. So if you add all of those up, you get 10. So our test statistic is 10. It had to beat 5.99. 10 does, so that is well into the shaded area. That is our calculated statistic. So we reject the null and conclude the alternative. And so we reject the null, that's A, B, C, D. Reject the null at 5%. And then part E is, we would say that we conclude that there is a different, like the color of the cars are not evenly distributed between black, silver, and other. So the distribution of colors is not the same between black, silver, and other. Okay. So, very much like everything that we've already covered, finding the test statistic is a little different. So, but we've got the null and the alternative hypothesis. You draw the picture and look up the critical value. You calculate the test statistic. You see if it ends up in the shaded or unshaded. You reject or fail to reject the null, and then you write up your conclusion. So in that way, it is very, very much the same as all the other problems that we have done. On 11.3, that's an ANOVA test. And really, you're going to have computer software figuring that out. I put it in the notes, like how to do it by hand, but you're never going to want to do that by hand. So an ANOVA is an analysis of variance. And what you can do with ANOVA is basically you're testing means of different sets to see if they are different. We're not actually saying this one is bigger than that one or less than that one. There's a different test for that. And again, that's a little beyond what we're doing. We're not going to calculate this by hand ever. What you're going to have to do for this course is interpret the results. So I'll give you the results and you'll have to figure them out. So if you didn't get this to load up on your computer, the ANOVA part of Excel, it's not a big deal. Don't fret. So, okay. At any rate, you put in the data into Excel and it kicks out a sheet when you run the ANOVA, and I posted a video on how to load it on and run it, but it gives you a summary like this. And so it finds the different averages, the variances, the sums, and the counts, and then between the groups, it does the same. All right. And so at the end of the day, though, it does give you, you're going to use the F distribution. So it gives you the critical value, which is right here. And then it also gives you the statistic, the F statistic on the F distribution right here. And so those are basically the two things. So again, if it exceeded 4.51, we would reject the null. Since it does not, in this particular case, we would fail to reject the null. All right, and then we would say the means are essentially the same. So if you take a look, I kind of break it down into its 5 pieces. So again, the null and the alternative for ANOVAs, we use an F distribution, which actually has 2 different degrees of freedom. And so that does get a little confusing. This is why we're using the Excel to basically do the work, or some other statistical software. You're not really going to do these by hand. And so basically the null is always going to be the same, that the means for however many, it could be more than 3, it could be 4 or 5 or whatever. Here we're comparing 3, but it's 4, 3 or more. It's not just 2. 2, we have statistical tests for 2. So 3 or more. And then the alternative is at least 1 is different. All right, so at least one of the means are different from the others. And so you can go through the steps of figuring it out are very intense and very tedious, so we wouldn't want to do that. So let's draw ourselves an F distribution, and I believe F is always skewed to the positive. Let me see. I'm less familiar with the F distribution. It's always positively skewed. So our F distribution kind of looks like, oh wait, that's where the, so positively skewed would mean like that. So a lot like the chi-squared. But there's 2 sets of degrees of freedom for this. When we look on there, it said our critical value on the readout. The critical value was 4.51. And then normally we calculate the test statistic, but it did that for us. So we got the 2.45. So our job is really just to interpret these numbers. So 2.45 would be here, which means we fail to reject the null. And then conclude that the means are not different. For what were the 3 things that we were comparing? I think it was sodium and condiments, cereals, and desserts. So the means are not different for sodium levels in condiments, cereals, and desserts. Okay. So the big thing with ANOVA is that you know that there is a test out there where you can compare more than 1 mean, or more than 2 means rather, 3 or more. And we're going to use a skewed distribution again, the F distribution, but we will not be doing the calculating. The calculating will be done with statistical software, like on Excel. So our job is to kind of interpret what's there and not not figure it out, and then do this and this. So again, it's a little more complicated, just like the chi-square goodness of fit test in 11.1, but it's also just exactly the same 5 steps that we've been doing with all of the hypothesis testing. So that's that. That's chapter 11.